Thank you very much. It's a pleasure to be here and to be able to speak a little bit on the work that we're doing on AI. So my name is Arthur. I'm working at the JRC, the Joint Research Center, as part of the European Commission. So for those that don't know, the JRC is the scientific body of the European Commission. So we try to provide information, scientific information to the member states and to the general public, for the member states basically for, and also for the Commission, but basically for supporting policy making and decision making. We do, basically the work that we do is part of the Copernicus Emergency Management Service. We do have a lot of different teams working in different topics. So for instance, we have teams working on topics related to population dynamics, so they're mapping population across the globe. We have other teams working specifically on different types of natural hazards. So the three ones that we're covering right now, it's floods, droughts, and wildfires. The one that I'll be focusing the talk today, it's on droughts, and as you can see from the previous presentation, there has been quite not so much attention to droughts, and I'll be spending a few slides on that to explain a little bit on the dynamics and why it's difficult to do that. The methods that I'm going to be showing there are a little bit, let's say, more simple to what we've seen, but it's also interesting to see that we can get quite nice results from methods that are not so, let's say, on the area of deep learning. I just wanted to start this presentation with a bit of theoretical review and kind of setting the ground on why this is relevant. And what I bring to you here, it's one of the latest reports from the World Economic Forum, which basically shows the, let's say, the interests or the main concerns that we have from leaders in the countries that are around the globe. So basically what they do in this report, they take a survey on country leaders, be that related to politics or in companies and so on, and they try to understand what can be the concerns that exist at the moment right now or in the near future. And it's interesting to notice that we have two of them that are basically very much in line with what we're discussing today in the short term, let's say in 2 years. So the first one, as you can see, is basically misinformation and disinformation, and this is strictly related to information that can be or not generated to AI. So you see in the second, on the 53% there you have AI information that can lead to misinformation or disinformation. And the first one instead is extreme weather events. So this is something that we've been covering in some of the talks right now, and it's also going to be the topic of my presentation here. When we move to the longer term perspective in 10 years, we see that, let's say, things related to the climate system or more to the environmental side, they perform a little bit more like in terms of relevance. So we see that climate change starts to jump ahead, and this makes sense. This is in the agenda of politicians around the globe. So we see also that we have this kind of actions right now. So we see different actions and different initiatives that are dealing with that. So we have, for instance, the Green Deal that in some extent is dealing also with extreme weather events, but we have other actions that are specifically tailored to deal with disaster risk management and so on, such as the Sendai Framework for Disaster Risk Reduction. And the other thing that is quite relevant to us, and also go back to the first session that we had today, that is the Early Warning for All. It's a new initiative by the World Meteorological Organization that they want to provide early warning for everyone in the globe in the next few years. And we have, of course, on top of that, the AI, something that we've been discussing and what we're seeing here in this conference today, that we have a large room to be able to explore and to use AI to support the decision. And we have different kind of initiatives around the globe that are going into that direction as well. So we have the NOAA AI Center for AI. We have also specific documents and guidelines that have been developed by, for instance, by the World Bank on how to use that to support disaster risk management and so on. Jumping now a little bit more to the topic of droughts and something that I mentioned that I want to focus here. So we know that we have this interest in extreme weather events, and we know that we can use AI to support that. But what is interesting to see is that the application of AI in drought risk management is quite low. So take a look, for instance, in the image on the top left of this slide. It shows basically the annual average number of people that is affected by the different types of disasters around the globe. And we saw a similar input also from the previous presentation that shows how different types of disaster can affect, particularly in the US, the economy, and how this is severe there according to the period that it has been analyzed. But if you take a look here on this image on the left side, on the top left, we see that flooding is the leading one, at least according to this report, that is at the global scale. And the second one is drought events. And we see also the drought, it's particularly relevant, and when we take a look also on the latest IPCC report, it shows the droughts, they are basically spread out across the globe, and it's particularly relevant in areas that might be more vulnerable, such as Africa, for instance. But we see that the application of drought concerning on the utilization of AI, machine learning, and so on, is only 1.9%. It's way lower than what it should be according to the potential representative, let's say, impact of droughts in our society and in the economy. So there's still a lot of room to expand in that direction. And what might explain this a little bit, and just to give a little bit background on why drought is difficult to use machine learning, is because it's a slow onset event. So it's an event that takes a long time to develop, and it's an event that can cascade down to several different areas of domain. So for instance, we usually start with precipitation anomaly, so it's purely meteorological driven. And we can see here on the right side how this accounting can be done by using the same indicator that is called the standardized precipitation index, but accounting for the different accumulation periods. It can be like 1 month that you're taking a look in the past, up to 12 months in the past. So you see for 1, 3, 6, and 12 months. And this has been computed using ERA 5 reanalysis data for basically the period of 2022 that we had the severe drought event in Europe. And you can see that the images, they are kind of locked in time, but you can see that they kind of show different extents and different durations and so on. So this is already the starting point. So for the most simple indicator that you might think of when monitoring droughts, you already have a kind of chaos situation in order to understand what is going on there. And as I mentioned, this is cascading down to other areas. So you start with the precipitation one. Then if the precipitation anomaly persists, you might have an impact in soil moisture that might cascade down to an impact in stream flow, and finally in groundwater. This can lead to impacts that you can see after the event, the meteorological event has already finished. So you might see, for instance, an impact in the stream flow or in the groundwater that might be impacting the agricultural productivity because we had a drought earlier on. We see here, just so an example, the image on the bottom left, it's the Po River in Italy, close to the city of Cremona, in 2022, and you see basically the bottom of the river. So you see these white areas are basically the river bank, and you see how severe it has been in that region there. So basically what we're exploring at the JRC, it's a project that is called the Enhanced Agroclimate Service that will basically try to combine the expertise that we're producing inside the JRC in order to be able to provide a more kind of early detection of drought events, not only in Europe, but also globally. So as I mentioned, it's a climate service, so it's basically to cover basically these 3 areas that you see highlighted there. There is disaster risk reduction, agriculture, but also water, of course. And the expertise that we're bringing from the JRC is basically coming from 2 different units. So the one on the left is the one that is producing periodically, roughly every month. They do a period of analysis of kind of 40 to 45 days, where they consider the potential implications of meteorological events for agriculture, so specific for agriculture. And we see that they provide this kind of summary reports where they show the areas that might be of concern. They call these as areas of concern, so more that is going to be emphasized in the rest of this presentation. And they also do a descriptive analysis of what can be this kind of, let's say, implication or impact from these potential events. And on the right side, we have basically the emergency management service, the one that I highlighted and the one that I'm working with, the team right now, where we provide information related to drought events at the European and global scale. So we produce several different types of indicators related to droughts, not just the standardized precipitation index, but other ones that are related to soil moisture, to vegetation anomaly, and so on. And also a combination of those, and depending on the way that we put them together to be a little bit easier for policymakers and the general public to understand them. But basically, we cover this kind of different dimensions of drought events, ranging from meteorological, hydrological, and also agricultural one. And what we try to do here, we try to combine these 2 information using a simple gradient boosted model. So we're trying basically to understand if with the information that we're producing at the JRC, we can be able to reproduce the information that we saw on the other unit that is producing the areas of concern. The areas of concern production, it's a very intensive work to be produced. As I mentioned, they do this kind of analysis for 45 days, and they have a team of analysts of around 10 people that are doing this kind of analysis. Some of the thresholds that they use might be fixed. Some of them are kind of subjective depending on the situation, how it's evolving and so on. So it's a little bit, it's not black and white definition of those areas. It's really like based on the expertise of the analyst. And what we try to do here is to see if we can train a model that is capable to kind of get this logic and reproduce these results by using the data that we're producing in terms of drought monitoring. Here's a little bit more on a description of what has been done with the model. I have here, for instance, some of the description of the different data sets that we did. I think I can potentially skip that for questions later on. But basically, the different types of areas of concern that we explored are on the upper part there. So we can deal, like, for instance, with rain surplus or rain deficit and so on. So they're basically like this kind of 7 ones that we cover, but the ones that I'm going to be showing the results right now are related to drought and heat waves that are more interesting to the topic that we're discussing now. These are the results basically that we have from the training, again, for the heat wave and drought events. You can see basically the results for the training data set and the test data set, or the out of sample on the right side. And you can see also since we're using a simple gradient boosted tree approach, we can also see like which kind of variables are coming out quite easily from the model. So how the model is perceiving the variables that can actually explain what we're seeing in terms of the drought monitoring. We see that also from these examples here that the model has a tendency to overestimate the areas. This is not so bad for us because the idea, again, here is not to replace the analyst, but it's kind of to provide a first guess, a first information to the analyst that they can use that a little bit easier to digest and use in their reports. But it's interesting to see that it's getting some dynamics quite interesting. So for instance, for the drought event here on the right side, the name of the variables are coded, but the first one is basically soil moisture anomaly. So it's really getting the information that might be relevant for agriculture. And the second one is the SPI, so it's the standardized precipitation index at the accumulation time of 6 months. Here just some visual interpretation of the results. So on the left side, we have basically the areas that are defined by the analysts. And on the right side, we have basically the results from the model. We can see that there's kind of a nice matching, but again, it's an interesting way to see that it's kind of conservative in some sense. So it's kind of overestimating the areas that the analyst has defined previously. This is somehow interpretable in some sense because we can see which kind of the factors that are basically leading the model to the results that we're seeing. So here on the right side, here on this slide, we have a little bit better the representation from another example related to heat waves on prediction of the model. So we have on the left side the actual product defined as areas of concern coming from the analyst. On the central part, we have these 2 plots that are coming from the reanalysis product that we're using to feed in the model. And it's basically getting the 2 most important variables as identified to the model. And on the right side, we have basically the output of the model, so the prediction performed by the model. And we see that it makes sense, you know. So we have basically 2 of the things that are extremely relevant for a detection of heat waves in this case. So the first one, it's related to the pressure level, so the mean sea level pressure or the pressure or the mean sea level pressure anomaly over the domain that we're analyzing. And the second one is the temperature anomaly, of course. Similar results for droughts. Again, it's performing kind of similar, but again, it's overestimating again. So we saw also from the confusion matrices that this is basically what the model is giving us right now. But we can see here again the influence on the variables that are more relevant that I mentioned before. And this is the similar approach that I showed just to show how this compare actually to the results that the analysts were producing. So this is an event again for 2022. In this case, we see that the model is performing a little bit like it's not able to capture very well the extent that has been defined by the analyst. So this is it's still like under investigation to understand like how this has been done. And as I mentioned, there's still a little bit of subjectivity in trying to define the areas of concern as coming from the analyst. So it can be that this is playing a big role in this particular prediction here. But we can see also here the factors that are leading to these results. So we see the SPI6, the negative anomaly covering the parts of North Africa and Morocco, and also we see the strong negative soil moisture anomaly in the Iberia Peninsula, like southern Portugal, Andalusia, and also again in the region in the North Africa. So basically, just to conclude, to say like what we've done. So we developed this kind of hybrid XAI-based model, hybrid in the sense that we're using the expert knowledge coming already produced by analysts and so on. And we're basically combining these into a framework to be able to try to reproduce this particular knowledge that is generated at the JRC. This has some advantage. So first, we can reduce the time that analysts are going to be spending in order to go through all the data and all the processing. So this can give a first guess, which they can then go a little bit more in depth into this kind of results to see if this makes sense or if this does not make sense. And also we can do this basically at the daily level. So we can, in theory, produce these at the daily scale by using the information that we're collecting from the reanalysis product. This, of course, is not going to substitute a report that has all the technical description and now the analysis that the analysts have to do in order to understand the potential impacts to agriculture. But this can be, of course, a very interesting tool for the early monitoring of drought events. So we can, for instance, incorporate this into our drought monitoring system and provide this kind of first early detection of drought events based on expert knowledge from this kind of approach here. In terms of research, we're basically tackling two, let's say, frontiers related to drought events. So the first one is the detection in space and time of droughts, which is something that it's quite difficult for us to be defining what is a drought, where it ends, and how it starts. And the second one, it's developing this kind of tool and applying this kind of tool for disaster risk reduction and disaster risk management. Again, this is a tool that we had some discussion also on which kind of method we should be using and so on. We decided to go with a tree-based technique because it would be a little bit easier to convey the message and show the interpretability to the analysts. So this is something that is fundamental. If we would be going with a kind of a deep model, it would be a little bit trickier to be able to convey this kind of trust in the model. So this is a little bit more clear to see and to convey the message to the analyst, as it is also transparent. So we can also easily kind of open the model and see how the decisions are taken and why this is actually being done. Finally, since we, of course, are part of the JRC, and I mentioned that we have this kind of, we provide information to have this kind of policy relevance, this kind of work, of course, can have policy implications as well. So it can, for instance, support the Water Resilience Initiative. It can also be used for the climate adaptation strategy, or also support other actions such as the EU Civil Protection Mechanism, the Common Agricultural Policy, and also, of course, the early warning for all, as I mentioned, if we manage to move these also to the early warning, let's say, domain, which is something that we would like to explore in the near future. This kind, just to complement also in the policy relevance, this kind of detection also of drought events can also be fundamental, for instance, for mechanisms that are already in place in the EU, such as the Solidarity Fund. So this is a fund that member states might be able to activate depending if they are being hit or if they're being under conditions of natural hazard that might be leading to some impacts on the country. This kind of tool can support this kind of analysis. So we can kind of say that, okay, a drought event is going on. We can see basically for how long and also kind of track the movement of that in space by applying such kind of tool. So I finished my presentation here. I'm not sure if I'm in time or not. So.
Thanks a lot, Arthur. We are running slightly late on time. Maybe a quick question from my side. When will your analysis be part of the EMS Copernicus program? Any plan to have that integrated?
Yeah, that's a very good question. Yes, we're planning to basically wrap up this scientific article right now. And we want to have also this kind of external revision by doing that. And the idea then is to incorporate these in these two ways that I mentioned before. So the first one is to provide these as a first guess of the areas of concern to the team that is developing and writing those reports. And the second one is the incorporation into our global and European systems to have this kind of daily track and daily evolution of the detection of drought events by using this kind of AI system. Yeah, we're planning to do that, let's say, in the course of this year. Hopefully, we're planning to incorporate these at least on our side on the EDO and GDO. That is the drought monitoring part.
Excellent. Thanks a lot. Looking forward to it.
Thank you.